Hi everyone, welcome to my class. Today, I'm going to talk about the process. First, we will learn the difference between program and process. In addition, we will learn parent-child process relationship and how to get the process ID and parent process ID using system calls. First, I'm describing a program. What is a program? Let's see the picture. You can see the main components in the computer systems, such as CPU, memory, disk, and kernel. A program exists in the disk. We have already created several programs using VI editor or integrated development environment, for example, Visual Studio Code. Normally, we make a program source code that is human readable text file and then compile the program source code to convert into the binary machine code that is computer readable code. In this picture, the program is the binary machine code. That means the binary machine language instructions that the computer can understand. Program inside. A program is a file containing various information that describe how to make a process at runtime. This information includes the followings. Number 1, binary format identification. It describes the format of the executable file. Number 2, machine language instructions. This means the algorithm of the program. Number 3, program entry point address. It describes the location of the instruction start point. Number 4, data. Values used to initialize variables and literal constants used by the program. Number 5, symbol and relocation tables. These describe the location and names of the functions and variables. Number 6, shared library and dynamic linking information. That means a list of shared libraries and the path name of the dynamic linker that should be used to load this library. Number 7, other informations. When a program is executed, the kernel loads the program into the memory. At this point, we say it a process. So we can say a process is the instance of the computer program. The kernel allocates memory space for program variables and set up data structures to record various information about the process, such as process ID and so on. We can create several programs that can be existed in the disk. Several programs can be loaded into the virtual memory. In other words, when the program B is executed, the kernel loads the program B into the memory. Therefore, several processes could be existed in the memory. We call it multi-processes environment. From the kernel point of view, processes are the entities the kernel should manage. The kernel must allocate the computer resources fairly among all processes. This is a picture showing the structure of virtual memory space. When the system boots, the kernel is loaded into the kernel space. If you run a program, the program is loaded into the user space. The program loaded in the memory becomes the process. Linux system can have multi-processes, as you can see. A process is divided into the several parts. Let's read from the bottom. Code, data, heap, and stack segment. Once again, code, data, heap, and stack segment. Code is the instructions of the program. Data, the static variables used by the program. Heap segment. Memory can be dynamically allocated at the process runtime on this area. This area is called heap or heap memory. And next, stack. The stack is dynamically growing and shrinking as functions are called or written. I'm describing this picture once again because this picture seems to be a little bit complicated. This picture shows the structure of virtual memory space. When the system boots, the kernel is loaded into the kernel space. You can boot or reboot your computer system using power on-off button or on your Linux systems if you are system administrator. After that, the operating system, that is to say kernel, is loaded into the kernel memory space. If you run a program on your Linux systems, the program is loaded into the user space. The program loaded in the memory becomes the process. Linux system can have multi-process environment. A process in the memory is divided into the several segments: code segment, data segment, heap segment, and stack segment. Code segment is also called text segment. In this code segment, there are the instructions of the program, that is to say, the algorithm of the program. In the data segment, there are the static variables used by the program. In the heap segment, heap memory space can be dynamically allocated during the process is running. The process may use the system calls related memory allocation. The static segment can be also dynamically growing and shrinking as functions are called and returned. A process can be create a new process using the fork system call. As you can see in the picture, the parent process called the fork system call, the kernel created a child process by making a copy of the parent process. The child process inherits most of the parent's data, stack, and heap segments. The program code can be shared by the two processes. The child process goes on to execute a different set of functions in the same code as the parent. The child process inherits most of the parent's attributes. However, the child process may not want to receive the inheritance from the parent. The child process uses the exec system call to load and execute an entirely new program. An exec call removes the inheritance from the parent. That is to say, the child process creates new segments based on the code of the new program. Each process has a unique process ID. Parent process has its own process ID. Child process has its own process ID. The process ID is a positive integer that uniquely identifies the process on the system. The first process is started by the kernel at booting time. The process is called Init Process. On Linux startup process, several parentless processes may be launched to carry out various daemon tasks. These processes are called daemon processes. Daemon processes normally are assigned the process ID between 2 and 300. On 32-bit Linux system, the process ID limit 32767. On 64-bit Linux system, the process ID limits about 4 million. When a new process is created, it is assigned the next available process ID sequentially. Once it has reached the maximum value of process ID, the kernel resets its process ID counter to 300. When booting the system, the kernel executes the program file /sbin/init and created a special process called init. The init process has the process ID number 1. Therefore, it is called the parent of all processes. All processes on the system are created by init process or by one of its descendant processes. The init process cannot be killed, and it terminates only when the system is shut down. The main role of init process is to create and monitor a range of processes. A daemon is a special purpose process that is created and handled by the system. Normally, the daemon process is started at system boot and runs until the system is shut down. Daemon process runs in the background. syslog-d is the example of daemon processes. It records messages in the system log. httpd is also the example of daemon processes. It serves web pages using HTTP protocol. This picture shows that the parent process has its own unique process ID, and the child process also has its own unique process ID. How can we get the process ID? We can use the get process ID system call to get the process ID of the child process. Therefore, we have to make a program containing the get PID system call and then run the program. The program becomes a child process. At this point, the child process is running and calling the get process ID system call to get its own unique process ID. Each process has a parent-child relationship. Once again, parent-child relationship. A process has a parent process because the parent process created the child process. So, each process has a parent-child relationship. We have learned each process has a parent-child relationship. So, how can we get the process ID of the parent process? We can use the child process using the get PPID system call to get the process ID of the parent process. Therefore, we have to make a program containing the get PPID system call and then run the program. The program becomes a child process. At this point, the child process is running and calling the get PPID system call to get its own unique parent process ID. A process can find out its own process ID using the get PID system call. The get PID system call returns the process ID of the process. The return data type is PID_T system data type. The process can find out its parent process ID using the get PPID system call. The get PPID system call returns the process ID of the parent process. The return data type is PID_T system data type. A process can terminate in one of two methods. One is by requesting its own termination using the _exit system call. The other is by being killed by the delivery of a signal. The kernel may send a signal to a process, or another process with suitable permissions may send a signal to a process, or the process itself may send a signal. Signals are called software interrupt. The arrival of a signal informs a process that some event or exceptional condition has occurred. Until now, we have learned the concept and attribute of program and process. In addition, we have learned how to get the process ID and parent process ID. Okay, that's it. Have a nice day and see you. Goodbye.